Thank you very much, Natalia, and thank you very much, Stefan. It's my great honor to be here. Today, I'm going to talk about overcoming limitations of metal organic frameworks. This title sounds like I'm doing such a great things or something special, but I didn't mean it. I believe our daily research activities are just a continuation of the effort to overcome the limitation of this field and to move forward to the better. So today I'm going to talk about what we are interested in and what we've done in this field. Okay, so let me introduce from the first topic, deconstruction. Okay, the destruction chemistry. Metal organic framework is composed of inorganic and organic species. So it means that it can be the very good precursor to prepare another material, such as metal oxide or carbon-related materials. So in our laboratory, we try to understand the mechanism of transformation of metal organic framework when we burn the many types of metal organic frameworks. So we try to test the many types of metal organic framework and to prepare the many interesting materials. But finally, we realized that we don't need to burn very fancy, expensive metal organic framework. So based on our understanding, we developed the much cheaper and properly unstable metal organic framework to make the material what we want. So I want to introduce representative examples. Actually, we can prepare the nanoporous metal oxide. Okay, as you can see here, this structure is hierarchically porous material. To make this kind of a hierarchically porous nanoporous metal oxide, we don't need to prepare the very stable metal organic framework. So in this case, we use the aliphatic ligand instead of aromatic ligand, and then we can prepare the properly unstable metal organic framework. And from the synthesis, we realized that that this aliphatic ligand, in this case, adipate is decomposed at low temperature to form the organic vesicle. And this organic vesicle acts as a porogen. And at higher temperature, this organic vesicle is evaporated. Then we can obtain the hierarchically porous metal oxide. Next example is that we can mimic the preparation of a graphene by using the coordination compound. Okay, as you can see here, we successfully synthesized the mesoporous graphene, which have a highly crystalline structure. Okay, what we did in this study, we just select nickel EDTA. Nickel EDTA is just very simple textbook compound, right? But during the thermolysis, we could know that nickel zero nanoparticle is formed. And this nickel nanoparticle acts as a catalyst for CC cleavage of EDTA. And also it can act as a catalyst to grow graphene on the surface. Then finally, we can obtain the graphene structure. Just after simple wet etching, we can obtain the beautiful the graphitic mesoporous graphene. So based on the mechanism study, we could understand the many mechanism of the transformation mechanism of a metal organic framework toward the functional, the nano-structured materials. Next topic is that development of a new synthetic method. Okay, so first, the method is microfluidic. Okay, microfluidic system. Okay, this setup is quite simple. As you can see here, we can use TFA tubing, and we can make the background flow with the oil, and we can inject solution of precursors. Then it can make the micro drumlet. And each micro drumlet can act as a single reaction vessel. So from this system, we could synthesize the various types of metal organic framework. For example, in the case of H-CUST1, we can prepare the quantitatively just in 10 minutes, okay, with a very high crystallinity. If we design more smartly, then we also can prepare the core shell structure without workup the process. We just sequentially prepare the core shell structure. And next system, next synthetic, the method is mechanochemistry. As you know, we use the many types of metal organic framework in many applications. But at somehow or at some point, metal organic framework should be degraded. And at some point, we cannot use it anymore. But if you think about the degraded, decomposed material, that solid still contain metal and ligand. So our thought was that how can we recover or reconstruct this the decomposed metal organic framework by using mechanochemistry. So we studied with MOF5 first. Okay, we easily prepared the decomposed structure of a MOF5 in 3 different phases, and by just a simple neat grinding and aging in small amount of a DEF solution, then we successfully reconstruct the MOF5 structure like this. We also can extend this method to other types of metal organic framework for mesoporous MOF, zirconium-based MOF, and GIF. Okay, so we prepared the original structure to decompose like this. As you can see here, this structure is totally non-porous material. Then after just a ball milling, then we can obtain the reconstructed metal organic framework. Okay, if you are interested in this topic, and tonight, Hong-Gyu Lee, my student, will give a presentation, poster presentation. So please visit him and talk with him. Next topic is that flexible MOF. Okay, I think the most beautiful properties of MOF is flexibility. We try to construct the new types of a flexible MOF, and also we want to understand, okay, those flexible nature. Also, we want to find the proper applications of it. So we conducted many experiments in many ways, but recently we successfully synthesized the 2-dimensional copper-2 MOF with a tetrazolate. Just by simple the heat treatment, we could obtain the copper-1 MOF. Okay, still the crystallinity is retained, and whole copper-2 is transferred to copper-1. And we can see that the structural transformation, and this structural transformation can be explained by hinged square tessellation. Also, this topic will be presented by my student tonight. So if you are interested in, please visit him. Okay, among the many kinds of experiment or study in the flexible MOF in our laboratory, I want to introduce one interesting example, hydrogen isotope separation with flexible MOF. As you know, deuterium is very valuable species. However, it's very hard to separate because the similar, identical, the physical chemical property with hydrogen. So still, by using the conventional method, the selectivity of a deuterium over hydrogen is very low. So we need to find another method. But theoretical chemists suggested that, okay, we can use nanoporous material to separate deuterium over hydrogen. Okay, that concept is quantum sieving effect. Okay, so there are 2 kinds of quantum sieving effect. One is kinetic quantum sieving. The other one is chemical affinity quantum sieving effect. Okay, let's see kinetic quantum sieving effect first. Okay, if you think about the property of hydrogen and deuterium, those have a different mass. It means that they can have different de Broglie wavelengths. So it means that that appropriately small pore can separate, okay, can act as a diffusion barrier toward the lighter hydrogen, okay, then, oops, hydrogen, then deuterium, heavier deuterium. Okay, so from the previous the research, people suggested that to see the kinetic quantum sieving effect toward the hydrogen isotope mixture, we need to have 3 to 3.4 angstrom pore size, pore size. Okay, and the other one is a chemical affinity quantum sieving effect. Okay, in this case, heavier the deuterium and hydrogen have different 0-point energy. Because of that, on the strong binding site, deuterium always win over hydrogen to make a strong interaction. So if you see here, MOF will be the perfect material to separate the hydrogen mixture because we can easily tune the pore size. Also, we can introduce strong binding site into the MOF. So since the quantum sieving effect concept was suggested 1995, okay, many types of nanoporous materials were examined. In 2018, MOF started to study in this field. So our thought was that to see the kinetic quantum sieving effect, we need a MOF which have 3 to 3.4 angstrom pore size. But instead of synthesizing this kind of porous, the nicely tuned the porous material, why don't you use flexible MOF? Okay, so we select the MIL53, and as you know, MIL53 has a very flexible, okay, breathing phenomenon. It can have the large range of a pore size, 2.6 to 8.5. Okay, and it showed that the transition between narrow pore to large pore. So here, our hypothesis is that during the breathing propagation, it should meet, at some point, it should meet 3 to 3.4 angstrom during the breathing transition. So we try to use this breathing transition for to see the kinetic quantum sieving effect. As you can see here, from the hydrogen adsorption isotherm, we can see the beautiful breathing phenomenon. At low temperature, very low pressure, it already showed at the large pore structure. But at 40K, okay, around 10 millibar, we can see that the transition, the breathing transition. So this is the right condition to see kinetic quantum sieving effect. And as you can see here, we obtained the TDS. And from at the low temperature, this structure already has a large pore. We cannot expect the kinetic quantum sieving effect. That's why the selectivity is not very good. But at 40K at 10 millibar here, okay, it has a large amount of a transition state. Then we can see that high selectivity. 3 years later, we examined further for the MIL53. As you can see here, for the hydrogen deuterium, we can see the clear, okay, the breathing phenomenon, right? But in the case of hydrogen, even at the low temperature, still we can see that the single step breathing phenomenon. But if you see that in the case of deuterium, at the low temperature, we already see the first transition, first the breathing. Then we can see the second breathing, right? So it means that after making the large pore, only for the deuterium, this structure is responsive. Then it can make very large pore state. So this is the first example to show that the specific isotope responsive breathing transition, especially for deuterium. Okay, but problem is that with the kinetic quantum sieving effect, Okay, kinetic quantum sieving effect is just based on the quite weak feed desorption. So only at low temperature, we can operate this system. So to increase the operation temperature, we need to consider the chemical affinity quantum sieving effect as well. So we try to put two kinetic and chemical affinity quantum sieving effect in one system. So we choose the MOF-74. As you know, MOF-74 has a high density of open metal site and very strong site. So we can expect the chemical affinity quantum sieving effect from the open metal site, but MOF-74 has very large pore, so we cannot expect the kinetic quantum sieving effect. So then we decorate the pore, okay, pore wall with the small molecule, and this small molecule can act as a diffusion barrier. Then we can expect the kinetic quantum sieving effect. Okay, so as we know, that there are many absorption sites, okay, hydrogen absorption sites on the surface of a MOF. First site can be the benzene ring. Second site will be the triangle of oxygen atom. Number three site is open metal site. And from the thermal desorption spectra, we clearly see that the three different sites. And interestingly, from the experiment of a 1-to-1 hydrogen and deuterium mixture gas experiment at high temperature, this is corresponded to open metal site. And open metal site, only deuterium can be absorbed. It means that high temperature, we can have very high selectivity. So if you see here, just by putting this KQS and CAQS in one system, we could see the synergistic effect, and we can have very high selectivity with the metal organic framework. To see that the chemical quantum sieving effect, we also tested at the Hofmann type metal organic framework. Hofmann type metal organic framework has a highest open metal site density. This is much larger, higher than MOF-74. So if you are interested in this topic, also please visit my student tonight, okay? And I think that still there is a long way to go to find that the ideal and optimum system with a MOF to separate the hydrogen and isotope separation. Okay, last topic is that MOF composite. Okay, to overcome or to improve the properties of a metal organic framework. Recently, many people try to combine MOF with other exotic materials. Okay, so we are interested in MOF and polymer composite and MOF and MOF composite. So let me introduce one example of a MOF polymer composite. Okay, here the polymer is PFPE. This is a highly fluorinated hydrophobic polymer. And interestingly, this polymer is a liquid phase in room temperature. It means that it is very easy to make a MOF ink at room temperature. Just by mixing with the MOF powder, we can prepare the MOF ink. And more interestingly, this polymer is a photocurable polymer. So just by irradiate the UV light, then we can solidify when we want, okay? So we can coat, we can write, we can print, and we can shape with this polymer, MOF polymer ink, okay? If we introduce aromatic pollutant sensing MOF into this MOF ink, then we can easily prepare the portable VOC sensor. Also, if we introduce temperature visualizing MOF into this MOF ink, then we easily can make a temperature visualizable sensor. But we are the more focusing on the MOF architecture recently. We can think about the two types of MOF architecture. It'll be lattice matching pairs, or it can be the lattice mismatched pair. Anyway, to make a beautiful single crystalline core shell MOF and MOF structure, we need to do many trial and error in experiment. So to avoid that, our approach is a little bit different. We collaborated with the simulation team. So what they do is that first, they screened out the pair of a MOF from the MOF database by considering a lattice parameter. So interestingly, from many pairs of MOF pairs, we could see that H-cust1 and MOF5 pairs. So there is no doubt to start with these pairs. And next, we need to consider the chemical connection point. Chemical connection point means ligand position and metal position. So if you make a slice through the coordination bond between the oxygen of a carboxylate and metal from the SBU, then if you see that the cross section, we can see that the position of a ligand and metal. This can be the potential chemical connection point with next metal organic framework at the interface. So this is the chemical connection point of a MOF5. This is chemical connection point from H-cust1. Then next, we superimpose these two positions, right? From the ligand from MOF, okay, metal from H-cust1. Then now we can tell that, oh, it can make a very beautiful interface, okay? It can make a coordination bond because it has the good lattice matching and the location of a chemical connection point. After considering the energy penalty as well, then we try to start the synthesis. It can increase the possibility of a synthesis. Okay, so we prepare the octahedron and cubic shape the H-cust1. Then if we grow the MOF5 as a shell, as you can see here, we can obtain the single crystalline MOF and MOF structure, H-cust1 at MOF5 core shell structure. If you see more detail at the structure of an interface, okay, as you can see here, it is very seamless interface. And if we try to crash this crystal through this interface, even we cannot do. It behaves like a single crystal. It means that at the interface, the MOF5 and H-cust1 make a very strong coordination bond. We can extend this the experiment to other pairs of a cubic system, H-cust1 at IR-MOF18, UIO67 at H-cust1, PCN68 at MOF5. We also can extend this experiment to cubic hexagonal MOF at MOF system. For example, UIO66 and MIL88B. Okay. Actually, if you consider that the reduced cell parameter, it showed that the quite good lattice mismatching, right? And by considering the chemical connection point matching as well, oh, we can try this pair as well. The result is like this. Octahedron, on the surface of octahedron UIO66, you can see that the growth of a MIL88B crystal, and we can see the star-shaped core shell structure. But interestingly, if you think about series of a MIL88, okay, MIL88 A, B, C is composed of a different size of different lengths of a ligand. It means that the lattice parameter should be different. So we can see that the larger mismatching from the MIL88C. However, we couldn't obtain the beautiful, right, core shell structure from this the large mismatching. But problem is that we successfully obtained this structure. What happened here? We understood this phenomenon. MIL88 is a flexible MOF. That's why if we consider that the range of the lattice parameter of a MIL88, it cover the UIO 66 lattice parameter. So it means that when we want to grow the flexible MOF on the robust MOF, this flexible MOF smartly tune the size, then okay, it can make a good lattice, lattice connection through the coordination bond. The last example is that 2D and 3D MOF-on-MOF. Okay, already, okay, there are already many 2D conductive 2D MOF, okay, reported, and we can have porous 3D MOF. Okay, by combining these two types of different types of MOF, we can think about many interesting applications such as a sensor. So we try to synthesize this 2D and 3D MOF-on-MOF structure, and we finally obtained this structure. If you see that the TEM image, it looks like just quite the physical mixture, but it is not. If you see that the interface between UIO 66 and nickel HHTP, you can see that the very well connected interface. So because of this, the interface, it modified the electronic structure, and also it showed at the different homolumo level. So when we applied this material for chemiregister to sensing the hydrogen sulfide gas, okay, this material always showed that the superior properties, response property over other types of the sensing materials. Limit of detection is just only 1.4 ppb, and also selectivity is very good. Actually, instead of conclusion, I want to share a little bit of our future direction. Okay, I think communication is really important between us, as well as between meta-organic frameworks. I'm very interested in what happened at the interface, and I'm listening the communication each other. And as a state of art in heterogeneous MOF, heterostructured MOF, I'm thinking of a mashup. In music, mashup means blending 2 or 3 songs, pre-recorded song, to create new song, right? We can mix up, mash up the masterpiece of Beethoven, Chopin, Dvorak, like this. We can do the mashup, the MOF5 from Yagi, H-1 from Williams, to make a real hetero interpenetrated MOF and MOF structure. Actually, this is already suggested by theoretical calculation team, and they prove that this structure is possible. But in experiment, it is very hard to make because we need to overcome the thermodynamic problem. But recently, we could see that some promising result. So hopefully soon, I want to share this result with you again. I'd like to express my sincere gratitude to all my group members, co-workers, and you. Thank you very much.
Thank you for a fantastic talk, especially like combining as a music. It's a brilliant example. I'm pretty sure that everybody is like free to ask questions. Laura?
Laura Gagliardi, University of Chicago. It was beautiful. Thank you so much. I mean, it's an amazing idea, but how practical is it? I think the goal is to try to push the field so that it can really be meaningful for very practical application. I wonder if now you introduce another degree of complexity that will make things much more challenging.
Okay. Yes. First, we are doing this for fun or as an art. And next thing is that actually we was doing this project with Samsung, and they tried to find a good material for sensing material. So we can combine these two different the material, like now it is just MOF5 and H+1, but originally we thought about the conductive MOF and the porous material. Then in between, they can make a pore, small pore, then selectively sensing the small molecule selectively. That kind of a thing is possible, but as you mentioned, this is quite hard to synthesize, but still we need to think about the applications.
Any more questions?
Great presentation, Professor. I want to ask, how do you tune that there's exactly one MOF inside the other MOF? And then what are the considerations you need to choose which MOF you would put inside and which one would be the one to grow outside? Thank you.
Thank you. Actually, this is can be possible because of our students' hard work. Actually, they try to find the very optimum condition. Okay, so first we prepare the core MOF. Then when we grow the second MOF, we need to find the proper concentration. Okay, so we test that concentration. At that concentration, mostly we do not obtain the shell MOF itself. It means that it is a quite diluted concentration. Then it started to, when we put the core MOF into the solution, at that time, it start to grow on the surface. So the concentration, the control is very, very important to, cover each core crystal. And second question was that, okay. So actually when the theoretical calculation team suggested the pairs, actually they don't consider that which one is a core and which one is a shell. But the experimental team can know, right? We need to consider that the stability of cores. For example, H+1 and MOF5. MOF5 cannot be the core for H+1 experiment, something like that. So if the stability is good, I think that the core shell core is possible. But it means that such the case, I mean the stability issue happened, then we need to select the core and shell carefully. Thank you.
Any more questions for the audience? I actually would like to ask one about your beautiful work about deuterium and the hydrogen separation. Mm-hmm. So then you do deuterium separation at high temperature. Are you going to deuterate as well as a framework by itself?
Oh,
for deuterium hydrogen exchange?
High temperature means 77 K. So it is not enough to the scrambling or exchange the hydrogen to deuterium on the ligand. So we didn't see that kind of phenomenon.
Deuteration process
No.
at all. Any more questions from the audience? Please go to the microphone. Thank you.
Thank you. Thank you very much for your talk. My question is, if you see some metal ion exchange or ligand exchange during your core shell synthesis. Thank you.
Thank you. Yeah, always I receive that question. Yes, we think some amount of some amount of a metal can be exchanged in the surface, but still this structure maintained. So I think that there is no problem to grow the core shell structure, and also there is no problem to implement our the strategy. But we do not exclude that the exchange phenomenon.
If no more questions, because I don't see it, let's thank Professor Moon one more time for fantastic talk.